and I'm really excited to be here to give this guest lectures on the topic of learning structured world models from physical interactions and for the robots to do better physical interactions in the real world. And the goal of today's lecture is that by the end of today's lecture, you'll be convinced that we should add structure to our learning systems. And with a suitable choice of structures and models of the environments, we'll get much better sample efficiency and generalization capabilities for real-world manipulation tasks. Some examples, as I'm showing here, including the manipulation of granular objects, deformable object, fluids, as well as there's an example of making dumplings using a lot of different tools. So start with the motivation. The question is, how far are we in achieving human-level robotic manipulation capabilities? We have already seen a lot of examples, especially in the drones or self-driving domains, where the robots has been on par or sometimes surpassing human capabilities, like, for example, the Boston Dynamics humanoid robots performing backflipping. And also, for example, in the self-driving, although we haven't seen a massive deployments of self-driving cars in our daily lives, the field has progressed a very long ways over the past few years, and we have seen some robot taxis in San Francisco. But we are still very, very far away of achieving human-level capabilities in performing physical interactions with the environment. There are just some typical examples people currently deployed in the industry, where the robots typically focusing on relatively simple pick-and-place tasks for objects with relatively simple shapes. But we humans can do much more than that. We can crack eggs, spread butter on a piece of bread, making dough, and making sushi. All of these capabilities goes far beyond the reach of the current robotic systems, where humans is interacting with deformable objects, with objects with high degrees of freedom. We're also making long horizon plannings of doing tasks that requires multiple steps. We also know how to correct from errors. For example, if things go wrong, we know how to correct our mistakes and getting back to the correct path. And I would like to argue like one of the key enabling factor and also one of the key gaps between robots manipulation capabilities and humans manipulation capabilities is this intuitive models of the world, where we humans can effortlessly predict how the environment is going to change if we apply a specific actions. For example, looking at these two examples, although we humans are manipulating objects of different materials, one is dough, one is a pile of onion pieces, we can predict intuitively how the dough will deform and how the onion pieces will move around. And it's exactly this kind of predictive ability that allows we humans to plan our behavior in order to achieve a specific target configuration. Here is how the system generally works. For example, we have the world. The world is give this kind of planner some observations, and this planner is trying to plan some action to execute it in the world. And this planner internally has these intuitive models. These intuitive models takes a current observation and action as inputs and trying to predict how the environment is going to change. And this predictive model can help the planner to plan its behaviors in order to change the state of the world to the agent's desires. So in order to make this kind of predictive model, there are generally two ways of doing it. The first one is to learn the model from data, which we can roughly categorize it as model-based reinforcement learning, and which I'm pretty sure has been covered a lot also in this course. The general framework of model-based reinforcement learning, especially model-based reinforcement learning from visual observations, work like this. So typically what people currently do is trying to map the visual observation into some latent vectors and learn neural dynamics model over that latent space. The benefit of it is that it can learn from partial observation and handle systems where the underlying dynamics are uncertain or unknown. There are success stories like Mu0 or controlling robots from pixels. But the challenge of it is that people typically just think of Z as just one single latent vectors, which is unstructured and limited in terms of generalizations. For example, for objects that like doughs or granular objects, when humans are looking at them, we're not thinking of them as just one single latent vectors. We have good structured understanding about these internal components and trying to imagine their internal interactions. So talking about the structures, arguably the most structured way of modeling dynamics is based on physics. Essentially F equals ma. This is arguably the most structured way you can represent the environments this morning, Warp have talked about a lot of like different ways to model the dynamics of the interactions. And it has excellent generalization capabilities. We also have a lot of success stories along those lines. But using full physics-based models typically requires that you have the full state information of the environment, which is sometimes very hard or even impossible to obtain for like real-world complicated manipulation tasks. For example, manipulating like a pile of onion pieces, like it's very hard, impossible to estimate the state of each and every one of the onion pieces. Or for buttoning your shirt, you only have to know the local interactions of the region near your button for you to actually do the task. Whereas for physics-based model, you actually have to know the full state of your clothes before you can actually do this buttoning process. So on the left is model learning, and on the right is actually structures in the models. So my research aims to bridge the gap and get the best of both worlds, trying to learn models with the structures inspired by understanding of the structure and physics of the environments, and trying to use that models for us to do the downstream planning tasks. Let me make the problem a little bit more specific. Here is our objective functions defined over the observation Y and the action U. And we have to think about three most critical constraints. The first one is what should be the representations of the environments, and how we can imagine the observation Y into the representation Z. And then is the dynamics model. Essentially, we have this predictive model that maps from the current Z and the actions into the next Z in the next time step. And the third will be the actions, like given the current representation, how can we come up with these action signals to minimize this objective function? One key things in this formulation is the choice of Z. And the choice of Z actually passes through the entirety of the entire optimization process that has a profound impact on the generalization capabilities and structures of your overall systems. So I will show like what should be the right representations and what's their implications about their structures. Then we'll also show that the right choice of representation can give us better generalization capabilities and sample efficiency. And specifically in this talk, the majority of the work will be about using particle as the representations for the environments, where your particles can represent the general geometry of the environments, as well as the interactions between and within different kind of objects. Specifically, we are using graph neural network to model the dynamics of this type of particle systems. And we call it graph-based neural dynamics model. Here is how it works. We have a graph that has 3 nodes and 3 directed edges. The node set V and the edge set E together is our representation Z. Then we have like each edge, for example, pointing to from point B to point A. We have an edge encoder that takes the information from the sender B and the receiver A to derive a representation for that edge EK. And then we'll, for each node, we will aggregate all the representations on edges where node A is the receiver. And together with the information on node A, we will update the information on this node to derive this updated representation for that node. Then we can define like different types of objective functions on this graph-based neural dynamics models to supervise the parameters and train the parameters within this neural network. Here, the objective function could be how good you can predict into the future. One thing to highlight is that the edge encoder and the node encoder are shared among all edges and all nodes. So it can naturally generalize to systems that are larger than during training. So here are some examples. Here on the left is the ground truth. On the right is our model's open loop predictions. Open loop, by open loop, what I mean is that the input to our systems are only the particle information on the first frames. Our model can make stable future predictions over a long horizon. Here's another example where there's a gripper trying to grip a cuboid. And the third example is trying to shake a box of fluids. Here we assume like the container is the actuation of the container is fully actuated. So we know its location and we're predicting the wave of the fluids. Like I mentioned earlier, the node encoder and edge encoders are shared among all nodes and all edges. So you can naturally generalize to more particles than during training. Here we show our system can generalize 2 times more particles than during training. Then we use this dynamics model. This is a forward model. Remember, our goal will always try to help the robots to do the control task instead of just learning the forward predictive model. Here we are showing that combine this neural dynamics model with a model-based planning framework, we'll be able to come up with a sequence of actions that shapes a box of fluids, such that when the countdown goes to 0, the shape of the fluids will match the targets shown on the top left. Here's another example where we're trying to grip the deformable form. Here, the decision variables are the position, orientation, and clipping distance of this parallel jaw gripper. We also tested the framework in the real world, trying to grip these deformable class systems into the target shape. On the top is a T shape, on the bottom is a tilted shape. And here are the manipulation results. But these are already results we obtained in 2019. So we are doubling down on these directions. But first, we want to understand, so why can we do these real-world experiments? And the key is that it actually to do sim to real transfer, where the model is actually learned from a basic physics-based simulators. But in the real world, we do 3D reconstruction to obtain the state of the environment and do online adaptation to estimate the parameters of the stiffness of these deformable objects. But we don't have a physics-based simulator. They can simulate everything around us. So we are asking the question, can we remove the dependency on the physics-based simulators and directly learn the model from real-world data? Like ideally for much more complicated tasks. So then, as we are already working on elastoplastic objects, so we are thinking about why not just push it all the way to the very, very complicated tasks, which is trying to make a dumpling. Dumpling making is actually very challenging. It involves a very long horizon, manipulation steps. And during the middles, you are also using different kind of tools. For example, like tools like your hands, or for example, rollers like a knife or cutters. And inspired by our human ways of actually making the dumplings, we are coming up with a set of 3D printed tools that's trying to extend the capabilities of these parallel jaw grippers. And these tools are actually have different type of actuations. Some tools are actually actuated, or for example, the grippers, they can open and close, or the spatulas, they can open and close. Some are not actuated. For example, the pressers and punctures, they can just press and rolling into the dough. So some with higher degrees of freedom, some with less degrees of freedom. So we spend a lot of effort actually trying to designing this set of tools to making sure it can work reliably. And here is actually our setups. On the left is actually our workspace. So we have 15 different type of tools, and we have this tool areas. On the corner, we have 4 RGB cameras looking at the environment. And in the middle is actually our workspace. And we do not use any simulation at all. Everything is done in the real world. So what we find is that with just 20 minutes of real world collected data for each tool, we can actually obtain the data that is actually super good for us to learn a good dynamics model. Here is actually our visualizations of our predicted dynamics models. On the top row is our prediction. On the bottom row is what actually happens in the real world, which is essentially our visual reconstructions of the interaction process. You can see our model's predictions is actually pretty well aligned with the ground truth. So why we only need 20 minutes of data? This is because we still use graph-based neural dynamics models, where the node encoder and edge encoders are shared among all nodes and all edges, which is a natural sparsity like structures in the systems to allow this type of sample efficiency. Here's another example shows the pressing comparison between our model's open loop predictions and the ground truth. There's another example shows the rolling where the areas of the dough will actually be enlarged. And then we integrated this system together, have these predictive models, and using this model to do either model-based planning or policy learning. And we'll be able to integrate it into the system that can make a dumpling out of a dough using these 15 different tools. What's interesting in this video is that during this manipulation process, there will be a person constantly perturbing the robot from doing its job. The robot actually has to be robust to this type of external disturbance. The humans are actually, for example, pinching the dough, pressing the dough, making the dough in different irregular shapes. The robot has to make has to take feedback from the environment and make real-time decision on first, what type of tool to use, which is a discrete decision. And then, given that tool, what type of action to take, which is a continuous actions. So this is essentially planning both at the task level and also at the motion level. Here the human is just so annoying, like trying to just constantly mapping the robots, and the robot is very like robust to this external disturbance. Here's what's interesting. After robots cut a circle out of a skin, the humans shows no mercy, destroy everything. The robot knows it actually has to start from the beginning, start from the scratch to really do the whole process before it can proceed to the next stage. What does this mean? This means is that our systems is not only like robust to perturbations within each task stage, but can also be robust and be able to like retrieve back to some earlier stages in order to continue with this type of tasks. In the end, the robot will place the dumpling fillings into the dumpling hook and then close the dumpling hook to make a dumpling. So we are also showing that this neural dynamics model not only can help the robots make dumplings, it can also do some other more basic tasks. For example, this is trying to come up with plans to make different type of like shapes of like a dough. Here's one example of making a letter O. The robot will first actually automatically decide what tool to use. For example, this symmetrical grippers to get the round shapes of the surroundings. And then the robot will choose like punctures to punch a hole in the middles to like get the shape of this O-like shape. It will punch again to make a larger hole. And the second example is actually to make a letter K. It's actually pretty interesting to actually see the strategies coming up by the robots. Here, the robot first chooses symmetric grippers, and then it will actually come up with a strategy that selects asymmetric grippers to get you the letter K. So I would say this is actually quite creative. Like even with humans, it's very hard to come up with this type of strategy to make a K out of original shape. So in this paper, we have also done population studies trying to show that our system can also generalize to like generalize to certain extents to other elastoplastic objects. And quantitatively, we compare with a range of baselines. Notably, the first baseline is actually compared with a method that's just do planning. Here we actually neural policy out of that. So by be able to neural policy, we'll be able to improve the efficiency drastically. Here the measurement is on first the planning time, which measures the efficiency, and also the human accuracy. By human accuracy, what we mean is that whether a human, like a subject, can recognize which letter that is. So our method is significantly faster than you just do online planning. And the second message is that we compare with the physics-based baseline, which is a material point method. We find that even with extensive system identifications using MPM, the model is still noticeably worse than our learned model that just learned directly from real interaction data. So we also show the learned model can be much more accurate than physics-based model, even with extensive sysid. So like following these directions, our lab just doubling down on trying to like show the capabilities of this graph-based neural dynamics model. So besides this elastoplastic objects, we also show that this system can be extended to like granular object manipulation. Here I'm just showing like one videos where these learned models that can assign particles over the foregrounds, describing the general distribution of the granular piece and trying to plan its behaviors to redistribute the granular pieces into different target shapes. You might already realize what the target shapes are. It's all the letter shapes from letter A to letter Z. This is actually not a trivial task. It requires some non-trivial redistributions of the object mass. And after the redistribution, you actually have to align with the fine-grained details to align with the target shapes. And our method can work very reliably to achieving those type of target shapes. And we have also shown like by using this graph-based neural dynamics model, you can handle the dynamics and interactions between multiple objects, especially for some very like actually practical tasks like stowing tasks. You'll be able to understand how your motions will influence these multi-object interactions and be able to use that predictive models to plan your behaviors in order to like stow objects into the shelf. So I want to just summarize a little bit about what we have talked so far. What we have talked about are using, for example, particles, key points, some compositional representations of the environment. And we combine that representation with graph-based neural dynamics models that is especially like helpful for objects that are compositional or with high degrees of freedom. It shows great generalization capabilities. For example, systems that are larger than during training, remember the shaking fluid examples, can generalize to like more fluid particles than during trainings. It can also generalize to unseen target shapes. For example, in the like letter rearrangements, like tasks, that during the data, the training data never have this type of A, B, C, D, F, G. It's actually very hard to like actually collect that type of data. The data are actually just randomly like pushing the piles around. You can actually generalize to those type of complicated target shapes that are unseen during training. In terms of sample efficiency, for each tools, we only require like 20 minutes of real-world data. The type of compositional structures really benefits for the sample efficiency. And also, by selecting the number of particles automatically and dynamically, you can use 10 particles to represent the environment. You can use 1,000 particles to represent the environments. The capabilities of representing the environments at different levels of abstractions actually can give you the great trade-off between efficiency and effectiveness. So this line of work using particles and graph-based neural dynamics model has mainly inspired two major lines of follow-up work. One line is actually scale this up for large-scale graph-based dynamics, like large-scale particle systems, intuitive physics, and also mesh-based systems. The other line of works that we have been able to inspire is actually trying to use like particles as representations for deformable object manipulation, like amorphous material manipulation, close smoothing, elastic material manipulation, as well as this benchmark that's trying to evaluate the capabilities to like interact with deformable objects. So what's next? So what I have shown are actually works we have already done like last year. So we have really pushing this down to show this capabilities of GNNs for a wide range of real-world manipulation tasks. And going from here, there are actually two major things that our lab have been really like trying to push forward. For this model learning, we are actually going towards the directions of building this coming from the control communities that could be great tools for us actually to do the optimizations where there's a neural dynamics model in the trajectory optimization process. In the first directions, I'm trying to like build this pure learning-based digital twins. We combine these graph-based neural dynamics models with Gaussian splattings. Like for people who are familiar with Gaussian splattings, you might think you might realize this is such a straightforward idea. Gaussian splatting essentially are just like a 3D like Gaussians in the 3D space, which is a type of Lagrangian representations. And particles is also a type of Lagrangian representations. They just very nicely like fit together. So in this work, also this year as CoRL, we're essentially using the Gaussian, dynamic Gaussians to track the objects over time, and using this tracking information for us to instantiate the particle sets that are evolving over time. And we subsample from the Gaussians to obtain the anchor points that instantiate our graph-based neural dynamics models. And then we'll be able to learn the models based on those anchor points, and then be able to do the future predictions. Here are actually some of the results. Here are the ropes. Like here are like the actions that are interacting with the rope. Here is actually our models like 3D action conditions video predictions. So the prediction is actually in the 3D space. You can render the predictions over different viewpoints. Here's another examples of interacting with this stuffed animal. Here are the 3 different viewpoints. And you have this pusher to push these models. And it's purely neural-based. Neural network is doing dynamics prediction and also doing rendering. And we actually construct a web interface where you can actually play with. For example, here, you can select the rope long. Here's actually the rope we obtained. Here is actually the Gaussian reconstructions of the rope. And the model is actually trained on the rope that are shorter. So it actually shows certain levels of generalization capabilities. This is actually generated 3D videos that are actually in the 3D space. On the bottom is actually the last frames of the predictions. And here we show that you can change different viewpoints. Here's from a different viewpoints, still the same push. You can predict the evolutions of the environment. And this just some other views. It's actually pretty reasonable. Obviously, you can make the rendering better by like doing shadowing, everything. But still, I think like this would be a very promising initial step of building this kind of pure learning-based digital twins of the environment. So this is on the model learning side. We are also like pushing forward on how to find the best and most effective ways of doing model-based optimizations using those learned models. Specifically, like we start with something simpler, like pushing the T. Like you can actually formulate this optimization problem. This is a trajectory optimization problems. You have your, for example, state representation Y, your action U, and then you have your objective function C that are measuring how far you are in terms of the distance between your current state and the targets. And we can just like actually write this problem in a simpler form where essentially it is trying to minimize some objective function F, where decision variables is U, and where U is actually should be sampled from some like input action space. And these formulations, if you really look at it, that F involves a lot of neural networks, obviously, in the middle. And this is very similar to what people actually do in neural network verification community. So what does neural network verification do? Essentially, what they do is trying to find the smallest amounts of perturbation they can fool your neural network. You have some objective functions, and the constraints are also the neural network. Here, like trajectory optimization with neural dynamics model is the same. You have some objective functions, and your constraints are also neural networks. So we are bringing some of the state-of-the-art tools from the neural network verification community, like Alpha Beta Cron, which is actually the winner of neural network verifications for us consecutively many years. And the key techniques of this neural network verification tools is trying to do GPU accelerated branch and bound in parallel. So it's a very efficient ways of trying to like propagating the bounds and trying to do branching over the input space. The general idea like actually is pretty straightforward. You are trying to like branching in the input space. You trying to estimate the lower bound and upper bound of each branch. And if one branch where the lower bound is already higher than the upper bound of some other branches, you can just like cleave that branch away. And you can actually do this kind of branch and bounds all on GPUs that is very efficient. So we actually have a poster. If you want to know more details, please come chat with me. So here is actually some of the results. Here, our task is trying to push the T from some starting locations to the targets. We have learned dynamics models that predicts the evolutions of this T when you apply a specific actions. Here, the initial configuration can change. The target configuration can change. There can be different numbers or different configurations of the obstacles. That's the benefits of using model-based plannings, where you do not have to like constrain your demonstrations. On the right, what we are showing is actually the plan trajectories using our branch and bounds planner. And then we are executing these plans. Here in the middle, we're just showing some intermediate representations, showing our state estimation, the next sub goal, and our model's plan, short horizon plans in order to achieve the targets. Here, one thing to note is that the targets, this black contour, actually indicates the lower sides of this T. So it might seem to be offset, a little bit offset, but actually it's attached to the targets very precisely. And here are just some more examples of pushing this T into the target configurations, where the number of obstacles can change, the configuration of the obstacle can change, then the target can change. And we compare our method with sampling-based planner and PPI, which actually is pretty good at doing like very scalable samplings of your action trajectories, whereas our method actually performs much better in this case. And we also show that this type of framework also can extend it to many other type of interactions. For example, this multi-object interaction between two L, which you want to merge them, and also show that this framework is applicable with graph-based neural dynamics models. We learn a graph-based neural dynamics model to predict the interactions between these different object pieces, which allows us to like sort them And on the last examples, we also show like this neural dynamics model can predict the dynamics of a rope. And then we'll be able to use this planning framework to plan the behavior to like feed the rope into the clip. So yeah, that basically is the end of my talk. I should thank all my collaborators. Like without them, it would be impossible to do all the work I have just shown. So happy to take any questions. Thank you.
Very nice one. When you go to like 1,000 particles, which is not much, it's like 10 by 10 by 10. How long does the planning take through that kind of state space?
Very good question, Emil. So we shouldn't think of the number of particles like 10 by 10 by 10 because that's essentially the type of representation as voxels. So voxel, I would say, is a fundamentally different type of representations than particles. But voxel is a type of Eulerian representation, and particles is a type of Lagrangian representations. The evolution of the environment for particles meaning the change of the location of the particles. But evolution of the environment for voxels actually means the change of intensity and values for each voxel grid. The representation are fundamentally different, and the modeling like class might also has to be different. So typically, like for many of the tasks I'm showing, we are not going to 1,000 particles. It's just maybe 80 particles, 100 particles. For many of those scenarios, it can be done very efficiently. You can do it maybe like 5 hertz in the closed loop planning loop. But 1,000 particles, it will be much slower, but we do not need 1,000 particles.
So I have 2 questions about generalization. You were explaining that the representation for nodes and edges, they're shared for the object. I just wanted to know for each new object, do you need to train it, or is there, let's say, I don't know, a variable or parameter that can detect if it's a deformable object, solid object, liquid, and it can generalize with, I don't know, set of training to a new formal object that is on screen?
This is very good questions. So that actually narrows down to like how do you actually instantiate the graph, and especially for like different numbers of objects versus new objects. So actually, for the success of graph-based neural dynamics model, you actually have to be careful in how you instantiate the graph. First, you want to make sure the sampling of the particles actually have a good coverage of the geometrical like shape of the objects. And you also want to make sure if there's 2 nodes between 2 objects, there will be some edge attributes indicating whether this edge is for particles within an object or between different objects. And the particles on the pusher, for example, the gripper, will also have different attributes than the particles for the objects. So in that regard, so by using like some attributes on the nodes and attributes on the edges, you will be able to like distinguish multi-object interactions and how the system should be represented. Like you need to have sufficient information for the model to make the sensible predictions. If there's ambiguities, you can run into trouble.
And the second question, you showed that you have multi-camera setup. Have you seen if it's generalizable if you change this into egocentric, for example, camera? Is it working still with the same, let's say, graph neurodynamic model that you trained with multi-camera?
Yes. So in our lab, or especially Munich, have a very strong emphasis. If we can go into the 3D space, we go into the 3D space, unless the task is just a pure 2D task. So because nearly all the models we learn are actually in the 3D space, such that if you have like different numbers of cameras, as long as you can have a reasonable like 3D like a reconstruction of the environment, you can just sample particles over there. But obviously, if a task that requires some views from the back, but you don't have a camera in the back, that's the system can like run into some weird situations. But that's not our issue. Because the task is challenging. You should add more cameras for the success of the task. But the fact that we are operating in the 3D space, we are less sensitive to the number and the location of the cameras.
Thank you.
Thank you.
Okay. Sorry, I would say that since you also have a poster, maybe we can put the other questions to the poster session because we do want to have time for the panel. So, and maybe also some questions can be asked during the panel. So let's thank the speaker again.